Good morning. So last time we discussed different categories of routing protocols, and we said that we have interior gateway routing protocols and exterior gateway routing protocols, and inside the interior gateway routing protocols we have distance vector routing and link state routing protocols. So this time we'll start by the first type, which is distance vector routing protocols. As I said last time, distance vector routing protocol using distance vector to select the best path. And this distance vector contains distance. So in distance routing protocols, we have to know the distance to the final destination between each node from the source to the final destination and the direction or vector that the traffic should be directed. So for distance vector routing protocols, for each source or for each router, we have to define the distance to all final destinations and the directions the traffic should be used or should be directed to reach to this final destination. Okay. And examples of distance vector routing protocols will be RIP, routing information protocol, interior gateway routing protocol, and enhanced interior gateway routing protocol. These are examples for distance vector routing protocols. So in the following, we'll discuss general characteristics or general requirements for distance vector routing protocol. Then we will specify a specific characteristic for each of these routing protocols. So at the beginning, all our discussion will be general for all distance routing protocols. Then we will discuss specific characteristics that differentiate between different routing protocols. For example, differentiate between the RIP and the EIGRP and enhanced EIGRP. For distance routing protocols, there is periodic updates sent to all neighbors. So the first characteristic or first thing in distance vector routing protocols, it uses distance and directions. Second, it uses periodic updates. So each router will build its own routing table and periodically will send this routing table to all neighbors routers. So the updates or the routing information exchanged between the different routers will be periodic. And this updates طبعا will be broadcasted. So for example, this router will broadcast this updates to all routers. Broadcasting means sending to all neighbors or all routers. And in these updates, we send the entire routing table is included in these updates. So the updates or the information exchange distance vector routing protocols, these updates have three main characteristics. It's periodic, so we send it in periodic, broadcast to all routers, and these updates include the entire routing table. So we put all the routing tables inside these updates. After exchanging this information, we need a routing algorithm to define the best path. So routing algorithm used to achieve certain task, and the main task of routing to select the best path to each destination. So the main purpose of a routing algorithm is to send and receive updates. So exchange updates between the different routers, send and receive updates. After receiving these updates and building a routing table, we need to calculate the best path. Then after calculating the best path and after the network becomes stable, we need to detect and react to every change in the network. So after building the routing table, after defining the best path to all destination, if there is any change in the network, we have to detect this change and react. Reaction here means updating the routing table and updating the best paths if it's required. Yeah. But this is the three main purpose or three main functions of a routing algorithm. And as I told you before, this chapter contains many definitions and many functions. But it's important to know all the definitions and all functions for each definition. A routing algorithm, it's a protocol or a procedure using to achieve certain task, and the main task here is to select the best path and make the routing. And this routing algorithm contains three main functions: send, receive updates, calculate the best path, and detect and react to any change in the network. Okay. Now we discuss this characteristic and this requirement for distance vector routing protocol. طيب, what is the main بقى criteria I can use to assess if this routing protocol is good or bad? Because here we have some conditions or some requirement for distance vector. طب, this requirement is good or bad? This protocols is good or bad? How we can assess or evaluate these routing protocols? There are four main points to assess or evaluate my routing algorithm if it's good or bad. First is the time of convergence, time to converge. And as we discussed last time, convergence means what convergence means. Hmm. Convergence means we reach to steady state. خلاص, all routing tables are the same in all nodes, and no one of the routers will change the routing tables based on the new information. There is no new information exchange between routers, and all routing tables are the same at all routers, and we reach to steady state. That is the convergence. But it's important to reach to this convergence very fast. The routing algorithm will be good or bad based on first time to converge. Will I need large time to converge, or it will converge very fast? According to the time needed until reaching to the convergence, it's one of the criteria that I should use to compare between different routing protocols. Second is scalability. Scalability here means how this protocol will perform if the network size become larger. So for example, some protocols work very well in small networks, but when the network become very large, the protocol performance will be bad. So according to how the performance will be in large networks, it means that if this routing protocol is scalable or not. Scalable, it will perform well in the large network. Not scalable, it will perform bad in large network and will perform good only in small networks. The second characteristic or second metric I can use to compare between routing algorithms is scalability. Is it good in small network and large network, or it's limited only on small network? Third is the resource usage. Does this algorithm need many resources, or will use many resources to define the routing or to find the best path? For example, does this algorithm need a large computational and large memory? So in this case, I will use resources, many resources. Resources here mainly refer to memories and CPU. Will I need CPU and large computational to define routing table and construct routing table and get the best path, or the calculations is simple? And also the memory. Do I need large memory, or it's not needed to have a large memory for updating routing table and calculating and running this routing algorithm? The resource uses, how many resources I will use, is also one characteristic. For example, some protocols you need large resources, some protocols need small resources. And last thing is the implementation and maintenance. Is it complex to be implemented, or it's simple? And if there is some error, it's easy to maintain this algorithm or to enhance this algorithm, or it's difficult to reinstall or maintain this protocol. These are the main four characteristics that we can use to compare between different routing protocols. For example, in your project, if you decided to compare between different routing protocols, first two things you should use. يعني, you should compare the time to convergence and see it will take large time to converge or no, and scalability also you can use. طبعا two other metrics, and for you in simulation it will be difficult to identify in simulation. But the first two metrics can be easily used to compare between any group of routing protocols. Specifically بقى for distance vector routing protocols, these are the advantage and disadvantage of distance vector routing protocols. The main two advantage is first two advantage are simple implementation and maintenance and low resource requirement. So from an implementation point of view, it is simple, and from a resources requirement, it doesn't require many resources. Simple implementation and maintenance because it's require يعني less complex to be implemented because the idea is simple. We discover our neighbors, we send the periodic updates, and we update the routing table and find the best path. Using the periodic updates makes the implementation of this algorithm is a little bit simple. And since this implementation is simple, we will use less resources, less memory, and less CPU to update a routing table and define the best path. But on the other hand, the disadvantage are first slow convergence due to periodic updates. So using periodic updates make the implementation simple, but on the other hand, makes the time to convergence large. So it's slow to converge because we have to send periodic updates many times until we identify all the network and know all paths and know all nodes. So we need these periodic updates. So these periodic updates will slow the convergence. And this طبعا periodic updates and slow convergence will reflect also on scalability. So due to the slow convergence and the periodic updates, these routing protocols are preferred to be implemented in small size network. So in large network, it will require very large delay to converge and it will require large amount of periodic updates. So it's not suitable for large network. It's more suitable for a small size network. That's limited scalability. So scalability is limited. It's better to be implemented in a small network. Third disadvantage is routing loops. Routing loops, we will define these routing loops later. But routing loops also due to slow convergence. Routing loops mean that the packet will be exchanged between group of routers and will not reach to the destination. Will be exchanged, and if router مثلا router 1 will send to router 2, send this forward this packet to the destination. Router 2 will send back the same packet to router 1, لا, send this packet through your interface to the destination, and so on. So the packet will go in the loop and will not reach to the destination. This happened because of slow convergence, because there is error in updating. يعني. For example, one link may be down from one router, but this router doesn't send the updates to other routers. So other routers will consider this link is still available. This will make routing loops. We'll discuss routing loops in details maybe at the end of this lecture or next lecture. But all three disadvantages based on periodic updates and slow convergence. But on the other hand, the positive side of using periodic updates are simple implementation and low resource requirements. Okay, these are the main advantage and disadvantage of a distance vector, and it's important also to know the advantage and disadvantage. The main steps now that we will use بقى to implement this algorithm. First step is the network discovery. Initially, when we restart our router or start our network from scratch, we initially start to discover our network. And we call this discover, it's called start because it's slow at the beginning. I only know or identify a directly connected network are initialized placed in the routing table. So initially I will only include my direct connected neighbors in the routing tables. Then I will see what I will have later in the next hub. But a router initial startup or initial network discovery is to add the directly connected networks to the routing tables. Okay. So here is example. If you have router 1, router 2, router 3, and this is the IP connected to this router, and these are the interfaces of this router. So each router, for example, at the beginning, router 1 will only put in the routing table the directly connected interfaces or directly connected networks. ف what's the directly connected network? I have 10.2.0.0 and 10.1.0.0. So I have only these two IP directly connected to me. So I will add these IPs to the routing table. I have 10.1 and 10.2, and this 10.1 I can reach to through FA interface and through S0 interface, and number of hubs to reach to this IP is zero because it's directly connected to me. So at the beginning, this first step, network discovery and initialization. This is the first initial step. Router 2 will include the direct connected IPs اللي هو 10.3 and 10.2 and the interfaces. This through S01 and this through S00 and number of hubs 0, S3 same. Add the directly connected IPs, interfaces, and the number of hubs. But this is the first start. This is the initial step or initial network discovery. I will add only my directly connected networks. Okay. Then after second step is to exchange this initial information. So if routing protocol is configured, then the router will exchange this initial information. After knowing my directly connected network, I will start by second step to exchange information with my neighbor routers. After receiving these updates at each router, I will update my routing table. Let's see second step. In first step is hub 0. I has direct connected routes, direct connected routes, direct connected routes. Now, this initial step or this routing table will be sent to R2 to R1. So R1 now will discover that there is a new IP 10.3 connected to router 2. So this new information, and what I know is that is connected to me. After exchanging information with R2, R2 sent to me its routing table. But its routing table contains 10.2, I already know it, not add. And 10.3 is new information for me. So I will add this to my routing table. And I will reach to this IP through S0 interface. But now the number of hops will be 1. Then I will reach to this IP after one hop. After going to R2, then from R2 to this IP. This is new information for me. For R2, it will collect two new information. It's already know 2 and 3, but from R1, it can be connected to 10.1 through router R1 through one hub, and from R3, it can reach to 10.4. It will collect these updates from R3 and R1, so it will add the other two new IPs. R3 طبعا will receive from R2 that there is 10.4. It's already known 10.3 and 10.4, and it will add 10.2 through R2. This is the second step, is to exchange information. فناو ال R1 collect information about 10.3 and R3 collect information about 10.2 and R2 collect information about both 10.1 and 10.4. Okay, this is second step. يبقى initial step put in the routing table my initial neighbors or directly connected neighbors. Then after exchanging these updates with the neighbor routers, I will add the new information. But does we reach to steady state or not? This convergence or not? This one round update, one update round, and this the first I built this and change this one with R1, this is with R3. So this is the first iteration here. Do we reach to the steady state or convergence or no? Hmm. Why? We still need to update more the routing table because convergence means what? means all routing tables at all routers contains the same information. خلاص all of us know the same information. طيب does it happen here? Is routing table at R1 contain all information? Still missing 10.4. I know 10.1, but still I'm missing 10.4. So my routing table is not complete. And routing table at R3 it has 3, 2, and 3 and 4. But it doesn't know any information about 10.1. But still routing table at 3 is not complete. So we still need more iterations or more updates. After receiving this update طبعا we update the metrics اللي هو number of hubs and add new information. If I have new information for example here this new IP, I will add this new information. If this information already exists in my record table, I will update metric. Here number of hubs for example. I will update my metric. Does it smaller than my metric so I can go through this path or it's larger? For example, here's this new information in this new IP, this routing table, this new information. But if let's assume this IP already exists, but I can reach this IP through R1 by one hubs, and for example, مثلا through R3 through two hubs. What I will include? One hub or two hubs? I will include the one hub because this is the best path. So no need to include that this IP I can reach to this IP through R2 with one hub and through R3 مثلا for example with two hubs. No need. خلاص I will add only one hub. But in some cases this information is already exists in my routing table and I will update only the metric. Is it smaller than my metric so this path is better or it's larger so no need to add this routes. But if this information is new from the beginning, I will, for example, add this for sure. Add this information. But information can be new, or the metric only can be new. This is the first iteration. After the second iteration بقى خلاص we already have this routing table. I will exchange this routing table again. So all this routing table will be sent again to R1 and all this routing table will be sent again to R3 and same R3 will send to R2 and R1 will send to R2. R2 طبعا complete خلاص 1 2 3 4 all complete. But after exchange R2 again with R1, R1 will collect 4 from R2. And here R3 after second iteration will collect 1 from R2. What we will have after second iteration here table 4 will appear back and through two hubs. I will go to R2 and R2 has one hub, go to R3. Already it's one hub at R1 at R2, so I will go to this IP through R2. And this IP will be added to R3 and also using two hubs because it's already one hub from R2 and there is one hub from me to R2. We increment one hub more. So now I will add 1 to 3 and IP4 to 1. And now what we'll have? These conversions or not? Yes, because all IPs خلاص and all information are exist in all routing tables. So all routing tables contain the same information. It means that the router conversions, we reach to the convergence. And the router contain طبعا to exchange information. If there is no information is found, then it means that we reach to the convergence. And if I send this router again, will I change anything? If I send this update again? No. If I send this to R3, will I change anything? No. It means that I reach to the convergence. No new information I will collect or no new information I will add to the routing table. Okay? Any question? This is how the distance vector routing protocol works يعني. طبعا its condition or mandatory condition is the convergence must be reached before a network is considered completely operable. Because before convergence, we may have some errors. We still have some missing information. But once we reach to the convergence, we can start communicate well and the network will be stable. Convergence must be reached before a network is considered completely operable. The speed of convergence بقى because we said that the time to converge is very important. طب the speed of convergence depends on what? What the main factors that affects the speed of convergence or time to converge. We have two main issues that affect the speed of convergence or time to converge. The speed of broadcasting the routing information and the speed of calculating routes. Because to reach the convergence, what we need to reach to the convergence? We need to exchange information until we build the routing table, and we need to calculate the best path. But to reach to the convergence, I have to exchange this information very fast. But this is the speed of broadcasting or speed of exchanging updates. And after exchanging update, I need to calculate the best route very fast. فإف I am calculating this route with slow with يعني with very slow speed of very low speed, it means that the convergence will be slow. If I calculating these routes very fast, it means that the convergence will be fast. So the speed of conversion or time to converge, time until convergence, depends on the speed of broadcasting information or speed of exchanging routing information and the speed of calculating the best path. These are the two factors that affect the speed of convergence. Okay. This يعني all previous discussion كان general for all distance vector routing protocols. Now specifically بقى for REP version 1 and REP version 2 we have طبعا periodic updates. So time in periodic updates mean time intervals in which router send out its entire routing table. So we have routing updates, each fixed or constant time interval. We will send the entire routing table and exchanges routing table between different routers. Even if we reach to convergence and we build our routing tables, we will periodically, every constant time interval, we will exchange these routing tables. But why periodically? Because maybe after some time, some link is down, some nodes become off. So to be conservative, I will exchange all routing table. So if there is new information here, for example, this IP is off, I will exchange this update periodically so other routers will know that this thing is off. So I periodically, this more conservative approach, I will periodically send the entire routing tables through periodic updates. And if there is any change in the network, all routers will detect this change, and after exchanging this information, we can update the routing table. In enhanced EIGRP or EIGRP بقى يعني the different routing protocols inside the category of distance vector routing protocols. ده بقى only exception for the distance vector routing protocol. It's distance vector routing protocols, but it's exception case because it's try to enhance these periodic updates. So in EIGRP, الrouting updates will be partial updates. So what we mean by partial updates, I will not send the whole routing table. I will send part of the routing table that may change. So this is first update in EIGRP. But again, it's still distance vector routing protocol, but this is special case from distance vector routing protocol. So this protocol made some updates in a distance vector routing protocol, but it's still distance vector routing protocol. But this special case or this updates it enhances in the routing updates by consider partial updates. So only part of the routing tables will be sent in the routing updates. So I will not send بقى full routing table like rep version 1 or rep version 2, I will send partial updates or partial of the routing table that has the new information. So it's partial updates or bounded updates. Bounded updates يعني limited updates. I will send only limited updates. Second thing is triggered updates. So it will not be periodic. I will not send constant by every constant time interval. Now it will be triggered updates. What we mean by triggered updates, if there is a change in the network, I will send the updates. If the network is stable, I will not send the updates. So it will be triggered by the change in the network. If there is a change in the network, it means that it will trigger the updates, send now the new updates, or send now the routing tables. It's triggered by the change in the network. It will be sent only when the network has some changes. So it's triggered update. And due to its triggered updates, so it's non-periodic. So its non-periodic updates is triggered only by the network change, and its bounded updates or partial updates. I will not send the full routing table, I will send part of the routing table that has the new changes or that has the new information. But this is a special case from distance vector routing protocol in EIGRP. Any question? Okay. For triggered updates, event, we name it also event-based updates. So if there is some condition or event, this event may trigger the updates to be sent. What is this events or what is this conditions that will trigger the updates to be sent? First is interface change. If one of my interfaces, for example, change or become down, so I have to send to all other routers this interface, مثلا, for example, is down or this interface is changed. So the first is interface change. Second is one route become unreachable. For example, if here I am sending to specific route to certain destination, and this route become down now, not connected. But if this route become unreachable, so I have to send to all other routes, take care these routes now become unreachable. Or if there is new route is placed in the routing table. If for example here we created new route or new route is added, new IP is added to the network or new route is added to the network, so I have to trigger the updates and send these updates. So the updates are triggered by new conditions or a new event, and this event can be drop one route or add new route or change an interface. But these are the conditions or the event that may trigger the updates to be sent. Also in the case of EIGRB, we're still in the EIGRB because it's in RIB, it's constant. The update is periodic. Okay. Any question? This بقى routing loop problems بقى in distance vector. This is يعني famous problem in distance vector protocols or periodic update protocols. And this problem comes from again the slow convergence and the periodic updates. How can this بقى problem happen? If we consider the same example R1, R2, R3, and we already built our routing tables and we reached to convergence. Okay, then IB4 goes down or becomes unreachable. This IB now is down, so I will R3 will discover, and it's directly connected to R3, but discover that this IB is unreachable, so it will remove this row from the routing table. خلاص, this IB is not reachable. طيب. البروبلم بقى is slow convergence, and this update will reach to R2 late or after some delay. But what will happen? R2 send periodic updates. R2 will send a routing table to R3. R2 هتسند الراوتنج تيبل بتاع R3. طب الراوتنج تيبل بتاع R2 contain what؟ الراوتنج تيبل بتاع R2 already still contains ال 4 10.4, and this will reach to 3 again because it's periodic updates. So what 3 will have, what 3 will do, will add 4 as a new information and will increment the loop. خلاص, I can reach to 4 through R2, and I have one hub with R2, and R2 reaches through one hub, so it will reach to this IP using two hubs. But this information is correct or wrong? Wrong. لأن أصلا I'm reaching to R4 through me, يعني R2 reaching to R4 through me. But it's blind address. I removed R4, but due to the slow convergence, I didn't send this information. Take some time to reach to 2. So I received the new information, the periodic updates from 2. I found that I can reach to 4 through 2. So I will increment the number of hubs and I add this information to my routing table. And I will consider this. I can reach to 4 through R2, and R2, suppose that I can reach to 4 through R3. طب what will happen بقى if you have packets بقى need to page مثلا from R1 to R4. R1 هيسند this packet to R2. R2 will forward this to R3, deliver this to 4 to 10.4. R3 will find I can reach 2 through R2, so I will send back to R2. R2 will search, لا, send through R3. So we'll go to loop. The packet will go into loop. This data will be, the packet is continuously transmit within certain routers and will not reach to the final destination. This is what we name it routing loops. Okay. What about the reasons of routing loops? There may be many reasons for routing loop. The first and most important one is slow convergence, because I didn't send the updates very fast to tell or to inform all other nodes that this IP or this route is down. So due to slow convergence, I added this information or this route again to my routing table by mistake. First, main reasons of routing loops is slow convergence, and there is may have some other reasons like incorrectly configure static routes. For example, I may by mistakes add مثلا this IP 10.4 by mistakes to the routing tables of 3 مثلا by mistakes, and instead of مثلا make a number of hubs 0, I make a number of hubs 2. So by mistakes, I add this information wrong. This information may cause some loops. Incorrectly configure routes, so I can make wrong routes, or incorrectly configure a discard route. يعني one route is removed but when I try to reconfigure or put this route, I put مثلا another route. I didn't remove the correct route. This is the main reasons of routing loops. The main one is low convergent, and the other is due to incorrectly adding new information. For example, incorrectly configure routes or incorrectly configure certain route or discard certain route. Incorrectly adding information or slow convergence. Right. What's the problem بقى of routing loops, or what are the effects of routing loop? طبعا excess use of bandwidth. I will consume bandwidth because the packet go in loop. So it will be transmitted and retransmit again between two routers or many routers. So it will consume bandwidth, useless. I am sending the same packet, useless. So it consume or use the bandwidth, large bandwidth. It consume also the CPU resources because I am receiving decode the packets and forward this packet again and receive the packet again and forward this packet again. So it will consume also the CPU resources. It will affect the network convergence, so we may reach to the convergence after a long time, and a routing update may be lost or not processed in timely manner because there is some يعني noise or some data exchanges very frequently in the networks. This may affect exchanging routing updates and make the network slow down. Okay, this is the reasons of a network loops and the effect or the impact of a network loops. Okay, any question? Here you need to know definition of routing loops, what is the reasons of routing loops, and what are the impact or effect of routing loops. How we can solve basis routing loops? We have four main methods to solve these routing loops. The first one and the most simple one is setting a maximum. What we mean by setting a maximum? We will add a new metric which is the maximum hop count. Okay, so the maximum hop count will be used to prevent routing loops. So in distance vector routing protocol, we use TTL or time to leave in the IP header. In each packet, in the IP header of the each packet, we'll put a time to leave. This time means how many times should this packet will be considered in the network before I drop this packet. For example, we will consider setting a maximum, we'll consider 16. The maximum number of hops to be 16. So the TTL will be 16. So when I am first time I send this packet, I will send with TTL 16. So this packet مثلا will go from R1 to R2. So TTL will be 15 at R1 because it's one hop. So go from R2 to R3 will be 14. طبعا due to network الrouting loops, what will happen? R3 will send back to R2 will be 13. R2 will send back to R3 will be 12, and so on. So I will go through the loop until TTL becomes 0. When TTL becomes 0, I will drop this packet. خلاص, remove this packet from the network. It will not reach to the destination. So I will drop this packet. So the first solution is setting a maximum or set maximum hop count. So what will بقى 3 do? Is this now 10.4 become unreachable? So unreachable for me, it means that number of hops 16. Number of hops 16, it means infinity. I need infinite number of hops to reach to this IP. But once this IP is unreachable, instead of removing this IP from the table and receiving these updates from other tables, so I will add it again. I will keep it on me, but with number of hops 16. It means that it's unreachable. And when I send my updates to R2, R2 will update it also 16. And R2 will send to R1, R1 16. 16, when I see 16, it means that this is unreachable. And even if I go through routing tables, the TTL or time to leave will be decreased until reach to 0 and the packet will be dropped. Okay? If I reach to 0, the packet will be dropped. Okay? And instead of removing this row from the tables and then by mistake adding it again after receiving these updates from other routers, I will keep it and put maximum, set maximum, setting a maximum number of hubs. Okay? This is the first method to avoid routing loops by setting a maximum. Any question? Okay, so let's stop here. Continue next time, inshallah.